Yeah, welcome everybody to today's colloquium. My name is Leon Röhlkötter, and from the IO quantum computing team, I will like to guide you through today's colloquium. Last year, Quantum BW was established as the state initiative for quantum activities in Baden-Württemberg in order to pool all the efforts on quantum computing and create an overarching umbrella brand that further strengthens the networks in Baden-Württemberg and makes them more visible. With this colloquium, we want to further promote the scientific exchange on quantum hardware and algorithmic topics in the field of quantum computing, and present the latest research, and also promote the idea of co-development of quantum solutions. Today I have the honor of introducing our speaker, Professor Marko Rancic from the University of Luxembourg. Just a quick overview of his bio. He finished his master's in physics in 2012 from the University of Niš, Serbia. I hope I pronounced that correctly. He received his PhD in theoretical quantum physics from Constance, working on the theory behind spin qubits inside of quantum dots. After that, he spent a few years at Total Energies, leading their global quantum efforts until he accepted an assistant professorship role at the University of Heidelberg in 2023. And since last year, he is now a tenured associate professor at the University of Luxembourg for HPC and quantum computing. Today he will give a talk with the title Quantum Computing in Physics and Chemistry and Optimization, which will focus on the recent advances in the field for tackling industry-scale cases on current-day hardware and the synergy between high-performance computing and quantum computing. So if you have any questions, please feel free to ask them. Also online, the questions can be posted into the chat. With that, I will hand over.
Thank you.
Have fun.
Thanks for the introduction. The outline of the talk is, first I gave a very short introduction to quantum computing. I asked my host, all of you should be more or less familiar at some level with quantum computing, so I hope I don't have to dive too deep inside the topic. The usual slide, what are quantum computers? Classical computers are composed of bits, while quantum computers are composed of quantum bits. A classical bit is in a state of either 0 and 1. When you look at your processor, when you look how your computer is processing, it's processing by having a very tiny, well, let's call it a wire, it's not really a wire, and this wire has current either flowing or not flowing through it, and this is your 0 and 1. Quantum computers are different. They operate on laws of quantum mechanics. Quantum mechanical objects, quantum mechanical two-level systems, they are not exclusively in the state of 0 and 1. They can be in the state called a superposition, which is a quantum mixture of 0 and 1. And often when you see popular talks about quantum computing, you say, qubits, they're in a superposition, the cat is dead and alive, the qubit is 0 and 1. But this is not what is really kind of behind the phenomena of quantum parallelism. And quantum parallelism, it's the parallelism in quantum computers which is allowing you to more efficiently compute something on a quantum computer that you would be able to compute on a classical device. There is another phenomenon that's called entanglement. What this entanglement means, it means that if you take two quantum mechanical objects and move them a universe apart, they are correlated. But more so, they are correlated in a way which doesn't exist in the classical quotation marks world. Meaning changing the state of one of those superimposed quantum mechanical bits instantaneously influences the state of the other bit. And this is a phenomenon which you don't find in any classical setting. And furthermore, this is the phenomenon which is between quantum parallelism. When people ask me, give us a 1-minute overview why quantum computing is better than classical computing, they say, well, you have all of these quantum mechanical bits, and you flip one of them, all of them will automatically follow. And this is what is called sometimes quantum parallelism. Various types of quantum devices exist, as you probably know well here. First quantum devices are quantum annealers. They're first quantum devices commercialized. They're called quantum annealers. They're very good, but only for solving one type of a problem, which is called the QUBO problem, or the quadratic unconstrained binary optimization problem. Now, the good thing about the QUBO problem is that it maps to so many other problems in combinatorial optimization that the fact that these annealers are good for a QUBO type of problem means that they can actually tackle quite a lot of other industrial relevant use cases. However, I'm not going to be speaking about quantum annealers. What I'm going to be speaking about are so-called NISQ, or quantum computers. NISQ quantum stands for Noisy Intermediate Scale Quantum Computing. Noisy, you understand. Intermediate scale, up to a couple of hundred, up to 1,000 on qubits and quantum computing. You understand? They are good for chemistry, physics, and optimization problems, which is basically the topic of my talk. Then there's also another specialized type of device, which is called the Gaussian boson sampling machine. They're very interested. I'm putting them here because they recently reached quantum supremacy with Gaussian boson sampling. Gaussian boson sampling is yet another quantum computational computing paradigm. It's good in calculating something which is called Hafnian of a matrix, and it's also very similar to quantum annealing. This kind of computing a Hafnian of a matrix has to do with a lot of other different industrial size problem, vibronic spectra of molecules, solving optimization problem, finding the maximum dense subset in a graph, so on and so forth. And then there's the holy grail, and this boundary, when we're going to have a universal quantum computer, keeps moving and moving and moving to the left-hand side. But the field has made quite some advances. A universal quantum computer is the same like a NISQ quantum computer with something called quantum error correction implemented. Questions of errors are going to arise very often, or in a few places in this talk. How is a universal quantum computer different from a noise intermediate scale quantum computer? It's in the way it handles noise. So a noise intermediate scale quantum computer would use special ways of operating qubits, using some post-processing of a result to give you a better result. While a universal quantum computer has quantum error correction implemented directly on the device, meaning you would put qubits in special spatial arrangement such that the overall level of your error is lower. But sadly, this still doesn't exist. Okay, and just, you kind of probably saw quite a slide like this. There are different approaches to building quantum computers. This is the quantum annealer, which is here, which you put on a chip holder. A quantum computer looks very similar to a quantum annealer when you look it up. So this is kind of where the compute happens. There are also specialized HPC devices which emulate what a quantum computer does. And there's some kind of an optical device which I found here for a picture. Good. This finishes the introductory part of my talk. Now to give you the outline. Part one is going to be more about chemistry, or chemistry/material science, so to say. Part two is going to be more about physics and quantum topology, and part two is going to be physics and topology. Part three is going to be optimization in this talk. So I kind of try to cover all of the use cases of modern noise intermediate scale quantum computing in this talk, at least those that I personally worked on. Okay, so first, part one, carbon capture. The work in carbon capture, which I did, deals with metals which are called metal organic frameworks. They're not really metals, they're metal organic frameworks. There's a metallic piece here, and this is a unit cell of a MOF. Okay, for those of you who deal with solid state, a unit cell is kind of a spatial pattern which you repeat throughout your space to build the material. This material has metallic clusters in here. It has organic benzene-like linkers, which you can find here. And the yellow ball, which you see in the middle, this is empty space. They're very hollow materials. These very hollow materials are useful for a number of applications. They're one of the greatest discoveries 21st century. And there is quite some efforts towards building a carbon capture technology out of these materials. Basically, you would use them like a molecular sponge, which would absorb CO2 from flue gas. However, there is one problem with those materials. They're extremely difficult to model. Okay, why? Especially when you add moisture to the problem and any kind of a practical industrial application of this technology, which involves hydrogen bonds on top of everything here, is going to make this problem very, very difficult to solve with, I'm putting in quotation marks, conventional numerical methods like density functional theory. The reason of this is multiple-fold. The metals which are here, they form a ligand bond. It is, depending on the type of metal which you use, very difficult bond to model. And furthermore, when you add water molecules, the hydrogen in the water molecules stick all around these materials, adding to the complexity of describing this numerically. So, because my talk is about quantum computing, of course, there is going to be a quantum computing part in how to treat this type of material. And now I want to introduce the famous algorithm which is called a variational quantum eigensolver, a bit methodically. So a variational quantum eigensolver starts from any type of a fermionic problem. What's a fermionic problem? Electrons in a molecule, something in a material, this is a fermionic problem. The fermionic problem is first transferred into a language which a quantum computer understands. You can write the fermionic problem with the first quantized Schrodinger's equation. But this is not a language which is easily to interpret for quantum computers. Quantum computers are very good in interpreting the algebra of something called Pauli matrices. So there's a very elegant mathematical transform which takes your fermionic problem, writes it from the first quantization to the second quantization Hamiltonian, and transfers it to the language which now a quantum computer can understand. This is the language of Pauli. Oh, now your quantum computer understands the problem. And this algorithm is a classical quantum, it's a hybrid algorithm, which you will see here. And basically, you will take your qubit Hamiltonian, which is a representation of the energy of your problem. Solving kind of diagonalizing this matrix gives you the energy spectrum of your problem. And you would prepare something called a trial state on a quantum processing unit. What is a trial state? It's an educated guess of your solution. Meaning you would do some kind of random operations on the quantum computer, you would measure this expectation value, and there is a very elegant principle called the risk variational principle in quantum physics, which would then tell you this expectational value can never be lower than the lowest eigen value of the problem. And this is coming in something called the min-max theorem in linear algebra. Then you would communicate this result to a classical computer, which would calculate the energy based on the results of the measurement on the quantum computer, and tell, oh, your trial state was wrong, you need to update your trial state, try these parameters as parameters of the trial state, and you would spin this classical quantum loop until you get to a solution. However, you remember how complex was the problem which I showed you. It's very complex. It's composed out of many atoms. It's composed out of many electrons. Quantum computers, which you have available currently, they cannot take even a unit cell of this size and put it on an actual device and perform calculations on an actual device. You need to make this problem more treatable for your quantum computer. Okay, and how you do it? There are different ways of doing it, but one way is, how do you put a large fumarate, a large molecule like a fumarate on the quantum computer? So there are methods which you can borrow from physics, which were borrowed from physics condensed matter physics, strongly correlated system physics, which you can use on this type of problem to make it more amenable to a quantum computer. Quite a lot of these methods have to deal with mapping your kind of original problem to something called an impurity problem, something similar to an impurity problem. problem, and then solving the impurity problem and preserving, kind of solving this mapping self-consistently. So one of those methods is called density matrix embedding theory, and basically you would solve the quantum many-body equation by having kind of the important part of the molecule where all the interactions happen, and this you would treat on a quantum computer, and having the non-important part of the molecule or everything else, which you would treat on a kind of on a low level. You would call it a bath, so to say. So you kind of, in a methodology sense, cluster the system to partition the system in cluster environment. You would compute something called the local density matrix of the cluster and solve the path in a mean field fashion on a classical computer. Okay? So now I'm going to tell you more precisely. This is
also known as the dynamical mean field theory?
No, it's not the same like the dynamical.
Not the same.
So it's density matrix, and the acronym is the same. So it's not dynamical mean field theory, it's density matrix embedding. It's different. It's very close to impurity to DMFT actually in the condensed matter. Physics, or this is what you mean, dynamical theory. It's not the same. No, it's close. It's the same idea. So to say, it's just that you solve the problem self-consistently. I'm skipping quite a lot of mathematical details on purpose. Here, you solve the problem self-consistently, but the condition how you map the initial problem to original problem is different. Actually, here you say that the local density matrix of your initial problem and the final problem needs to be the same. This is the point of DMET. DMET is a lesser known method, but is better adapted to quantum computers, so to say. So you would start with a unit cell, and now this is another picture of a unit cell, which is shown here, of these hollow porous materials. What you have here in blue, this is aluminum. What you have in red, this is oxygen, and what you have in black, it's carbon. So what would happen, and you can do DFT on this type of a problem, of a CO2 adsorbing, so kind of a CO2 molecule flies and absorbs this material. Where is the CO2 going to stick? Quotation marks. CO2 is going to stick, quotation marks, into the blue aluminium metal, and it has a lesser chance of sticking either to oxygen or to carbon. So you would perform your fragmentation, so to say. You would treat the CO2 and the aluminium with the quantum computer, and you would treat everything else as a bath, or in mean field, so to say. The real question, which you can ask is, how would you do this, so to say, fragmentation? Would you fragment each of those? Because also when you do fragmentation, it's a very difficult molecule to fragment. It's a very big molecule to fragment. So how would you kind of do the fragmentation here? Would you treat this CO2 and aluminum or as one fragment, or would you treat carbon monoxide as one fragment, and oxygen and aluminium as another fragment? What do you put here on a quantum computer? That is the question. Okay. So basically, you can compare what you have, and this is now, you take this model of CO2 going to a fumarate molecule, sticking to a fumarate molecule, adsorbing to it, and put it on HPC, meaning the results which I'm showing here are not actual results for actual quantum devices. This will come a bit later. These are results from encoding this problem in HPC. Okay, and you can say, okay, I have here the restricted Hartree-Fock. What is the restricted Hartree-Fock? The restricted Hartree-Fock is a kind of mean field method. It's a classical mean field method of solving this, and this is the red line. And then you can fragment aluminum as one fragment, solve the CO2 with a restricted Hartree-Fock, again a classical method, and solve the full-merged fragment, again full-merged fragment with a restricted Hartree-Fock method, and you would get the green line with the fragmentation. So you see that fragmenting like this, you will still have the same kind of relative minimum energy, but this dissociation barrier here will be larger. And then what you can try doing, you can try going from 4 qubits to 8 qubits to 12 qubits and to 16 qubits. And you see that strictly doing a fragmentation like this, increasing the size of your quantum mechanical fragment on a quantum computer, it's not really intuitive. Is it going to give a better or a worse result than a mean-field theory or than a classical kind of state-of-art theory. Okay. Good. But what you have here at the end of the day, what was here the point which I wanted to show, and again I don't have too much time to go too deeply into this problematic. I want to tell you that this DMET on a quantum computer can show us quite a lot about what type of a bond is being formed between CO2 and the full-merged molecule. Meaning, you have two ways in which you can do a fragmentation. You either fragment CO as one fragment and aluminum oxide as the other fragment, or you fragment CO2 as one fragment and aluminum oxide as another fragment. So I'm going to show you now that this is a more intuitive way of doing things, kind of fragmenting CO2 and aluminum and the rest of the full-merged as the fragment. But here's what's happening. When CO2, in this line here, is very far away from the full-merged molecule, CO2 has 22 electrons, like it should have. Aluminium has 12.02 electrons. Why 12.02? Because aluminium is forming a bond with the rest of the full-merged molecule. And 0.2 part of electron is transferred from the full-merged molecule to the aluminum. Okay. Now, as you bring your system, your CO2, together to the closer to the full-merged molecule, this here is going to happen. The CO2 is going to lose 0.18 part of an electron, but this 0.18 part of an electron is going to be a little bit distributed to aluminum and quite a lot to the rest of the fumarate. So in a sense, what is happening here is that when aluminum comes and absorbs CO2 in a carbon capture process, a very complex bond is formed, such that the part of the electronic wave function is not shared with the aluminum itself, but is shared with the rest of the organic fumarate molecule. So the take-home story for this is kind of choosing your absorbing material. You don't need only to take into account the metallic cluster which you're solving. You need to optimize the chemical composition of the entire material. Which is so you can also do the fragmentation. You can also do kind of the fragmentation in a bit of I would say in a bit of a different fashion. So you can say, okay, you can change the way you fragment between CO being one fragment and aluminum oxide being the other fragment, solving the aluminum oxide, where the oxide is coming from the CO2, and the story kind of pretty much I would say repeat itself, because the rest of the fumarate also kind of in a sense is going to change also its electronic number for 0.17, so even a bit more. So it doesn't matter how you fragment, it doesn't matter how you solve, it doesn't matter how you split the system. This bond which is being formed in the carbon capture process, it's a very complex bond, and it depends on both the metallic cluster which you have, but also on the rest of your very, very complex material. Good. So I'm out of time. Okay. So now I'm going to dive into a totally different topic. And this totally different topic is going to be about topological. quantum computing. Why am I speaking about this topic? There has been quite a lot of buzz about Microsoft's discovery of Majorana zero modes. So topological quantum computing is now a very, very hot topic that people are working here. I'm not going to go into the discussion about Microsoft's discovery in this talk. This is not the point of the talk. I want to show you how you can use quantum computers to study topological phases on current day devices. So what's the game with this Majorana zero modes? So everything that we see in the universe is composed out of matter. In the 20th century, Paul Dirac said, well, there is something called the antimatter, meaning every particle has an antiparticle. This antiparticle is coming basically with all the same properties, but has one property which is opposite to the particle of matter. For electron, this is the positron. It kind of has an opposite charge. However, in 1937, an Italian physicist called Ettore Majorana, he said, well, there is also this hypothetical particle which is exactly equal to its antiparticle. It doesn't have any opposite property. And this was a particle physics game for many, many years, until in 2001, Alexei Kitaev said, okay, this is not only a particle physics game, there is an actual physical system where you can embed particles and they would behave in a very similar way like Majoranas would behave. And when you hear about Majoranas and people working on Majoranas, they're not working on new particles or discovering new particles. They're actually finding physical systems in which they're encoding quasi-particles. These quasi-particles, they have some properties that original Majorana particles would have. So in the original paper by somebody called Alexei Kitaev, he would take a semiconducting nanowire, and this semiconducting nanowire would be indium arsenide, let's say, or something like that, or indium antimonide, even better. He would put this wire from B to B prime on top of a superconductor and put a magnetic field. And if certain conditions are met, at the edge of this nanowire, one electron would split and move towards the edges of a nanowire. And there's a Hamiltonian which describes this. So a Hamiltonian is basically W in this Hamiltonian is tunneling. So you would create an electron at site J and annihilate an electron at site J plus 1. You could raise the chemical potential of this nanowire globally with an electric field U. And delta, which you have here, would be the superconducting pairing. Why a superconducting pairing inside the kind of nearest neighbor tunnel cup of nanowire? When you put a nanowire on top of a superconductor, the superconductivity kind of leaks from the superconductor to the nanowire, and this is kind of described by this superconducting pairing. Why are they interesting why are these Majorana quasi-particles and these nanowires, blah, 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 interesting for quantum computing? Well, because you can build a qubit in this way, and it's a very different way of building a qubit. I warn you. And again, I won't have too much time to go into details, but you would take such two Majorana nanowires, put them one next to another one, couple them, and you will define a 0 and a 1 by the two Majorana nanowires being filled with the Majorana mode or being empty from a Majorana mode. This would be your 0 and 1. But very interestingly for this, and here an X with a line is a full Majorana mode, an X without a line is an empty Majorana mode. Meaning an empty Majorana mode doesn't have one electron which is bound to the two sides of the nanowire, and a full Majorana mode has an electron like this. This is your 0 and 1. So you would kind of control this hypothetical quantum computer by braiding. Now what braiding means is that you would kind of stock these nanowires, one next to another, then use an electric field to kind of suck out it into a perpendicular section of a nanowire and move the one edge of the wave function one around the other. And by doing this braiding operation, you would kind of do pi over half gates in these qubits. This is how you would loosely picture it. But this quantum computer would not be an ordinary quantum computer. This quantum computer would be a quantum computer where Clifford operations or pi-half operations of the quantum computer are ideal. They're not influenced by noise. It's very similar to quantum error correction, or it's partial quantum error correction in this case. And this is why people are working quite a lot on this problem. So this is a crash course in Majorana quantum computing, a very crash course. But the question is, can you take, and instead of what I want to show you here, I want to ask you the following question. Well, I can solve this Hamiltonian, this is the same Hamiltonian of a Kitaev nanowire on a quantum computer. And I can solve it exactly because it's unlike quite a lot of problems in chemistry or in material science, which are very complex to solve. This is a very easy Hamiltonian to solve exactly. And I can prepare an exact eigenstate, an exact wave function on this problem on a quantum computer. And then it's a question, did I create Majorana by doing that or not? And I leave you to read this Colbeck's and Rancic paper, which answers if I create a wave function of a system A on system B, did I actually create a system A quantum mechanical? It's a philosophical question, so I won't answer it here. But just to tell you what the approach here is, usually modern experiments with Majorana zero modes, they would start with the Kitaev Hamiltonian. They would find something which is called the BDG Hamiltonian, meaning they would find a system which has a more simple form of a Kitaev Hamiltonian in it, and this would be a system, and I'm again skipping through some details here, which would describe spinless fermions. And because spinless fermions doesn't really exist, you have to find a nanowire, which is this superconducting nanowire magnetic field, which embeds the same kind of mean field Hamiltonian in it. And then you ask yourself a question, if I cannot find Majoranas, why can't I find Majoranas with doing this trick? Because let me build back in something which I didn't tell you. Kitaev's Hamiltonian one here, it's a Hamiltonian which describes spinless fermions originally. Spinless fermions don't exist. So you're finding a system, a physical system, which has the same mean field Hamiltonian like spinless fermion would have. This does exist, but the approach here is not that. I'm not going to do what Microsoft people are claiming to do. I'm going to start with the Hamiltonian itself, and I'm going to encode the state of this Hamiltonian on a quantum computer and see how closely does this Hamiltonian behave like the Majorana Hamiltonian. I'm going to search for 8 properties of Majorana zero modes, which you need to find in any Majorana zero mode experiment. There needs to be a ground state degeneracy. It needs to correspond to the same mean field Hamiltonian. It needs to have a well-defined parity, which is a special quantum number, which topological quantum have. It needs to have a non-conserved particle number, because every time you have superconductivity in the picture, you're not conserving particle number in your system. And then it needs to have an edge correlation function, which is decaying with a chemical potential. And number 7 is very interesting, meaning that when you don't add an electric field, your Majoranas are exclusively localized at the edge, and nearest neighbor pairings at large value of the chemical potential. So first, I'm going to show you just a few figures. I don't want to dwell. There is a very nice, interesting part about noise mitigation in this problem, which is, I think, more interesting for the community here. But what you would do, you would take a free-side Kitaev chain, you would take 3 qubits, and you would exactly solve the Kitaev Hamiltonian by something called fermionic Gaussian states. You would encode this exact solution on your quantum computer, and you would ask yourself a very interesting philosophical question. Does this exact solution of the Kitaev Hamiltonian, which I just found and encoded on a quantum computer, behave the same way that the Majoranas would behave? So what you're seeing on the left-hand side, you are seeing basically a numerical diagonalization of a problem versus the Gaussian states on a fermionic Gaussian state, which is the exact solution of the Kitaev Hamiltonian, on Qiskit, on diagonalized on my laptop. So the first result looks promising because the X is on top of the blue and the red. This seems that the problem is the same. Now, doing research in quantum computing, you can go from executing your problem on laptop to executing on actual device, okay? And this is how executing these problems on actual device now looks like. Now the red is the same, like red and blue full lines are the same like before, but the X's are just coming from an IBM device which I asked to sample me the results of encoding the Kitaev Hamiltonian on a quantum computer. So you see what noise is doing to those problems. And by the way, these states where the arrows are pointing are what people refer to as Majorana zero modes. Often. So you would see that these states in the middle now actually are not influenced by noise at all, but these states on kind of, which are here, which are the Majoranas, they are squeezed by noise like this. But what's very important to understand is that what is protecting your quantum computing in the topological sense from noise is the fact that this degeneracy between these two states remains. And you see that in a quantum experiment with a quantum computer, the degeneracy between the red and the blue state here, meaning they have the same energy. The energy is shifted globally, but the energy is still the same. So you can change the picture to the mean field Hamiltonian. You can now probe, you can now take this and kind of try to reconstruct the mean field Hamiltonian from this. And now in this reconstructed picture, the Majorana states correspond to states close to zero energy. And if your states close to zero energy are degenerate, this in principle means you have noise protection. And here you see that you have two states which are close to zero energy, and that the noise on a quantum computer didn't do much to them. Those states which are split, which differ here, these states are called the topologically trivial states. These are non-Majorana states in this reconstructed picture. So you can also probe a number of properties of this problem. For instance, there is a quantum number of this problem which is called parity. I hope everybody understands the quantum number. Parity is a special quantum number, which usually exists when you have superconductivity somewhere in the picture. And for this Majorana type of problems, you need to have parity switches occurring at different values of your chemical potential. So you can take and you can see, okay, this is a classical prediction where parity switches should occur. Okay, this is from Hegde. The predictions are from Hegde. You can go to a quantum computer, sample, does your parity behave in the same way it should behave? And you indeed see that you have parity switches from blue kind of to red here, and full lines with squares, they are basically my laptop, and like lines with X's are samples from a quantum computer. And you can go on and on with this problem, treat different properties. Now I'm skipping through details because I'm running out of time, and I want to come to the interesting part, and this is noise mitigation. Okay, so eventually what happened with this problem is that I was contacted by researchers from IBM, and they told me, very interesting work. We can try to see, can we make this problem even better in terms of how basically much it's influenced by noise. So we performed various noise mitigation techniques. Here, which I don't want to go into detail, but it was a dynamical decoupling. It was then on top a purification method on top, and it was parity post-selection, all three combined together, and then a row of measurement error mitigation. And you see that in the blue line here, in the blue axis, in the blue squares, is the raw result, and in orange is the noise mitigated result. And this is already a 6 and a 7 qubit system, or it's a relatively large Kitaev chain. You can see that on the levels of the spectrum, it's almost an ideal kind of alignment with what you expect from classical theory. Full lines are again classical. Orange and blue are quantum computer, actual device. Blue is no noise mitigation. Orange is full noise mitigation. What you can also show very interestingly, and I don't have time to go into these results in so much detail because I'm also running out of time, and I still want to speak about optimization, but I'm going to explain this result here. What's happening, remember, in this Majorana picture is that you have a nanowire, and one electron splits into two edges, and these two edges, two halves of an electron become correlated. The left half becomes correlated with the right half. So you can define an edge correlation function like this, meaning is there correlation between the edges? And indeed, this means that there's a correlation between the edges. And as you add an electric field, as you increase the chemical potential, your problem stops being an electron, which is localized at two edges of a nanowire. It becomes more localized in the middle. So you have correlations between side of the edge of the nanowire and on the middle of the nanowire, like you can see here. Again, black is classical. Black lines are classical expected theory, diagonalization from my laptop. And orange and blue are outputs from actual devices. Good. And in the last 10 minutes of the talk, I speak about optimization problems. There's a very famous algorithm, which is the QoA. Who here knows what the QoA is? Should I skip the introduction to QoA, or take home message to the for the QoA? Maybe I'm just gonna show this slide. Take home message for the QoA algorithm. It's an algorithm which calculates a max cut of a graph. Meaning, I give you a graph, and this is a graph 1, 2, 5, and I ask you separate this graph into two subgraphs, such that the number of lines, the number of edges between the two subgraphs, it's maximized. This problem, it's an example of an NP-hard problem, or an NP-complete. It depends really how you frame the problem. But every time you hear words NP-hard, NP-complete, this means very, very difficult to solve classically. Okay? And how would you solve this problem in a quantum computer? You would take something called the adjacency matrix of a graph, which is basically the connectivity scheme of this graph, meaning vertex 1 is connected to vertex 2 with the weight W12. So you would put W12 between 1 and 2. Vertex 2 is connected to vertex 3 with 1, 3, and 4 with 2, 4, so on and so forth. You would take the weights of the adjacency matrix and map it to such of form of a Hamiltonian, HC equals Wij by 2, 1 minus sigma I, sigma jz, where sigma I, sigma jz are Pauli matrices. You would take this Hamiltonian and you would, again, like for the VQE algorithm, guess the solution. But the guessing of the solution here, it's a bit different. It's not totally random. You can derive the form of the ansatz, how this ansatz needs to look like, and it needs to have this form. It needs to have a layer of gates which are exponents of HC and of X gates. And you will repeat this ansatz over and over again, and the more you repeat this ansatz, the better your solution is on paper. And you would calculate the expectation value of this Hamiltonian with this ansatz, communicate it to a classical computer, and the classical computer will say, well, you are exploring your solution space in the wrong part of the solution space. You should explore it in this part of the solution space. And they will play the game. The quantum computer calculating expectation value, classical computer saying angles which you're using are wrong angles. You should use different angles. Try exploring this part of the space until you convert to a solution. However, mathematically speaking, what's the problem with the QoA algorithm? The biggest problem is, well, there are many problems with the QoA algorithm. The biggest problem is that for a graph which has 5 vertices, 5 circles, you need 5 qubits. There's no going around that. So for a graph which has 1,000, 2,000 problems, like a very difficult graph to solve, you would need 1,000 to 2,000 of qubits. And this is before I go into computational complexity detail and how many CNOT gates would I need and how would the optimization look like, so on. So this is why, and I did this work while I was working for a company. I was working for Total Energies, and they told me, great work you're doing in quantum computing, but we need to make it more applied. So I needed to find a way how to make quantum computing more applied. So I envisioned this alternative algorithm which is to QoA, but which uses exponentially less qubits than QoA to solve exactly the same problem on a quantum computer. And it's based on something called the quantum potent formula. First, in 1990, there was a paper from Potent claiming that the number of cuts in a graph can be calculated by taking a vector v of t, a graph Laplacian L, and a vector v of t. Graph Laplacian L is very similar to the adjacency matrix which I introduced before, but it has the level of connectivity on the diagonal. How do you understand this? Vertex 1 is connected to two other vertices. So you would put 2 on the diagonal. It has a weight of connection with vertex 2 as -1, and a weight of connection to vertex 5 as -1. So on and so forth. So it's very similar to the type of a matrix which you would use for the QAOA algorithm, except the main diagonal. And then the vector, which you would select vector x, you would take it like this: 1, 1, 1. If your edges, if your vertices 1, 2, and 3 belong to the first partition, and -1, -1, -1, if they belong to the second partition. And by doing this in linear algebra term, you would count for this type of graph Laplacian and this type of vector to the result to the result 3, 1, 2, 3 for this graph. Okay. So now I tell you how to do optimization with logarithmic limits. Okay. You would basically transfer L to the language of Pauli matrices, which you can do actually with exponentially less qubits. You would take the graph Laplacian, write it in the language of Pauli matrices. Then you would apply the following ansatz, which mimics basically what the vector does, which is basically just a diagonal gate. Very interesting point is that diagonal gates are very efficient to be implemented on a quantum computer. You would repeat until you optimize all values of theta 1 to theta n, and you would calculate the number of cuts in the graph with this formula here. And the partitions would not be in the measurement outcome, but in the phases of this exponential ansatz. Quite a lot of details which is skipped, I know, but let me tell you how it works. Okay, I have 3 more minutes. So what I'm basically showing you here was at the time the largest graph ever partitioned on a gate-based quantum computer. It's a graph of 32 vertices, and you can use only 5 qubits to do it on a quantum computer. This is a classical state-of-the-art method. This is the KISS kit on an HPC at this level, and this is actual device. Actual device 27, Guillen-Williamson 43, 25, 40. These results are going to become a bit better as the device became a bit better. I'm going to show you a bit later. But very importantly, and this is all the details which I'm skipping about. Actually, it's better to take this algorithm in terms of computational complexity. So it's not only better in terms of the number of qubits which it uses compared to QAOA, it also has a lower computational complexity in calculating this problem. And why is this the case? And I don't know what the computational complexity proves, but the QAOA has something which is very interesting. It has this parameter P, which is the phenomenological depth parameter, meaning how many times you need to repeat your ansatz in order to get to the exact problem of the QAOA algorithm, and the answer P is a very large number, which you can get. While the algorithm which I introduced here, it actually for deregular graphs has a depth which computational complexity which is proportional to V. So it's a much lower computational complexity compared to QAOA. And then you can do various benchmarks of this problem. You can ask yourself, how does this methodology which we are using actually scale with the density of your graph? And you see the denser the graph, the better the result. And these are random graphs, 32 nodes, so it's not an easy problem to solve. You can also show, oh, no, I'm skipping. You can also show even larger. Even larger problems. You can, for instance, show a 64-node maximum cut on a quantum processing unit, and the benchmark here is something called ELP, which is classically the best you can. Integer linear programming is classically the best method you can use to solve this problem. You can use this problem size. You cannot use it for better problems. So let's say for a density of 0.45, so density of edges. ELP gave 553 for a certain random graph, and a quantum processing unit gave for 546. And this is the only scale on which you can use ELP. when you have problems which are bigger than basically this, you're not able to use ELP anymore on those problems. And you can also go now, you can use a quantum simulator to go 128, 256, and the quantum solution is always 90% classical solution for really big graphs. Okay. And I'm slowly finishing. So doing this on a quantum computer is exponentially faster than emulating the same problem classically. And also what I maybe wanted to show you before we run out of time, this is the max-click problem. So you can map the max-cut problem to a number of combinatorial optimization problems. One of them being called max-click problem. So this max-click problem is basically you need to find within your graph an all connected subgraph. So it needs to be a subgraph, and every vertex of this subgraph needs to be connected to every other vertex. So for instance, for this graph, this is not a click, because not all vertices are all connected. For the black graph, this is not a maximal click. They are all connected, but you can define a larger all connected subset. This is a maximal click of the graph. So when you take this problem, map this problem to a maximal click, you can see that in 50% of the time for this problem, and we are speaking about 31 to 63 vertices, very large graphs, the quantum algorithm finds the exact solution. And I think I'm out of time. Took 4 minutes longer than expected. Okay, I'm going to leave you with this slide. I showed you some works on materials. I showed you some works about. I show you some works how you can do optimization. I show you some works how you can do topology. I want to just now take questions.
Thanks. Are there any questions straight away?
Yeah, so maybe going back to the Laplacian you introduced in the optimization problem, are the connection values, are they constant, or can they also be like...
They can be whatever, it works for both. Doesn't really matter. So they don't need to be, the question was, can the weights be -1 or something else? They can be whatever. And by the way, there's a very efficient way of finding this, transferring this graph to Laplacian to the language of power matrices. It works for any graph, any undirected.
So,
what's the intention of diagonalizing the BDG Hamiltonian with a quantum computer? Is this classically so hard?
You don't diagonalize the BDG Hamiltonian. You diagonalize the full Hamiltonian. Actually, so diagonalizing the BDG. Now this is the question about Majorana's and topology. Diagonalizing the BDG Hamiltonian, it's easy. It's an easy task, but it's cheating because it doesn't find you all of the eigenstates. It finds you only some of the eigenstates. The size of the BDG Hamiltonian, if you have an n-side K-type chain, it's 2 times n, while the full K-type Hamiltonian is 2 to the power of n. So the BDG Hamiltonian is kind of like a very cunning way of mapping your very big full problem to only few states and just solving these very few states. It doesn't give you the full spectrum. Hamiltonian. You just use it as a consistency check here, really, to see does it, you actually reconstruct how it's done. Physically, you would reconstruct the BDG spectrum from the full Hamiltonian, and trust me when I say I know how to do it, it was 2 months of my life to figure it out. But yeah, BDG Hamiltonian gives you part of the story. You cannot solve the BDG Hamiltonian on a quantum computer. You can just solve the full K-type Hamiltonian, and then after solving the full K-type Hamiltonian, trying to ask yourself the question, how does this map to the full? How does this map to this BDG picture that people have in supercomputing?
But the BDG gives you the answer, like where are the Majoranas, right? So
the BDG does answer you where the Majoranas are. You're entirely correct, but this is a bit different. You're asking yourself the question, can I encode these Majoranas on a quantum computer? So the BDG is there to check, is what you're measuring from a quantum computer okay in terms of what the classical theory is predicting or not? And the answer is yes, it's okay. You can reconstruct the picture from it.
Maybe I have a question precisely concerning the combinatorial optimization. Okay, so when you map this to a logarithmic number of qubits, so in the end, how can you make sure that you're still solving a discrete optimization problem?
Oh, this is a very good question. Because you relax it, actually. So when you look at this theta angles in these ansatz, if you put theta to be 0, it's 1. If you put theta to be pi, it's -1. So extremes of these ansatz correspond to actually the discrete optimization problem. All of the values in between are relaxations of this problem. So it's a very good question. You kind of map it to a continual optimization function, such that the extremas, the kind of the focal points of this optimization function correspond to the qubit problem, actually. Meaning in the extremums, in the optimum, it converges to the solution of the qubit problem. It's a very good question.
But that you also could do classically. So I can set up a relaxed optimization problem. This can be.
Yeah, it's just a question. It's just a question of memory. It's just a memory issue. Would you like to store these objects in your memory of your laptop, or do you want to store these objects in a QPU whose Hilbert space scales like to the number of qubits? So you can do it entirely classically, at least at the level of which I presented in this talk.
So there is a question from the chat. It says, thanks for the interesting talk. My question is, what is the advantage of this approach using quantum computing compared to the ab initio quantum chemistry approach, such as Hartree-Fock and post-Hartree-Fock?
Question is at the level of solving material science with metal organic frameworks, none whatsoever. Actually, when you look at the results. So the point of these results here, which I showed you, it's not that I tell you, it's better to use a quantum computer than restricted Hartree-Fock and this TCFD. It's to tell you, you can use this fragmentation method and get something which is of a comparable order of magnitude on a very complex industrial problem to a classical device. It's not this type of result here. It's not there to tell you, and you can obviously see it by the result, as I said. You kind of increase the number of qubits. It doesn't logically converge to either side. The only way you can interpret this is that the quantum computer is giving you something which is a good order of magnitude to the classical device on a very complex problem. But this opens a more delicate problem in anything which has to do with chemistry or material science applications of quantum computers. They're always like this. You're very happy when you get the result, which is on the same order of magnitude like the classical result. In my opinion, in this domain of material science and chemistry, we are very happy when we can have this. We are very far to be able to see practical. In this application or in pretty much any application, you can see over there.
Any more questions? If not, I want to thank you again for the great talk and to the audience for participating. On the 8th of May, we will have our next colloquium with Dr. Michael Marthaler from HQS on site here. He will present a talk with the title Quantum Computing Use Cases, Optimization and nuclear magnetic resonance. So somewhat related to what we've seen today. With that, I want to wish you a great day and see you soon.